Okay, welcome. This is two-dimensional motion and vectors again, and this is also still Chapter 3, Section 3. However, remember that Section 3 is now broken up into two parts. Part 3 was the first video on projectiles that did not have an initial vertical velocity, so there was no up and down velocity in the initial point of motion. So that would be like the rock being kicked off a bridge. Now we want to look at situations to where the projectile has an initial velocity other than just horizontal. And so whether we know what those velocities are or whether we have to solve for them, but these projectiles will now have those velocities and will travel a more true parabola than the half parabola of projectiles that are launched without that initial up-down velocity. In Section 3, I just copied the objectives over again. You can read those. This is a repeat of the one slide that we talked about, I believe, at the end of the previous Part 3 presentation. We can use vector components, which avoids some trickier math. Not that it's not, it's just beyond the scope of multiplying vectors. And the components will simplify the motion. Projectiles, remember, are any object that is launched, thrown, or will fall at some angle other than true up, down, or true out horizontal. Projectile motion is the two-dimensional motion that is under the influence of gravity. Remember, without gravity, objects will travel in straight lines. So says Newton, so says science. Paths of all projectiles in a gravitational field will be parabolas, and a parabola will never fully flatten out, just like in math class. And lastly here, projectiles will have an initial horizontal velocity, but our projectiles will now have an initial vertical velocity, whether it be up or down, it will have an initial vertical velocity. And I think most of the examples, actually, the vertical velocity is also in an upwards direction. So it's initially going up and out before it hits some sort of an apex and goes out and down. Okay, well, this is pretty grainy. This is a screenshot from, I think, a video. And this was initially what we worked on, if you look at this from the previous presentation, where this is just literally, I think, here, let me activate my pen. Here we are. This is literally just free fall. And so we have a rock. It is falling straight down. And we are solving some information about that. And we actually solved this question here. So that was just free fall, indicating that what happens if you just let something go and it's able to fall. And we had covered that, and that was a review of free fall, where we can reactivate those Unit 3 models. Adjusted for free fall, of course, where acceleration is due to gravity and with or without an initial velocity. And we talked about this. What would happen to objects in that were propelled horizontally without gravity? Well, that would be, what was that? Hang on. I do not like that color. That is fairly light. So without gravity, everything is horizontal. If you have no Vx, then it's only, so if Vx equals 0, it's completely free fall, it's going to fall straight down. But if it has Vx and gravity, then we get the parabola, we get actual projectile motion. And we solved this one as well. This was the rock thrown off the 100-meter cliff. It landed with a range of 95 meters. Remember that term, range. What speed was it thrown? This again is a screenshot from a video, probably in the same series. And it just goes through exactly what we went through, maybe in a different order. It looks a little bit different, but all the equations are identical, I believe. And it shows how to solve, and you solve for the time initially, which was, let's see, right down here, sorry. I'm writing in black and that's not going to show up. So initially there we solved for the time, and the time led us solve for the x velocity. Yes, that's exactly what we solve for. Oh, just a note on the notation. Let's go all the way over here to the left. VO. VO. VO is the same thing as VI, V initial. This is just a V naught, if you will. That's just a different type of subscript. Either VI or VO, they're very common. They're interchangeable. And it just depends on what website, what physicist, what book you look at, whether they use the O or the I. I haven't really seen too much notation other than that. Okay, so projectiles and parabolas, a little bit more on that. Now we're going to be talking about, and I think this, boy, this looks familiar. Yes, this is a review again. So we're going to be talking about out and up and out and down. We've already talked about out and down, so we're going to now talk about the out and up part of the motion as well. And this will be due to gravity, as far as why it stops going up and why it falls back down again. Remember that the less air resistance affects the motion, then the truer the parabola will be. So we're going to basically make air resistance negligible for the foreseeable future. So we're not going to have to really worry about that particular resistance. Interesting note, we already talked about that if it starts and stops at the same height, we have the advantage of actually then looking at the fact that half of that trip is actually just the rock being kicked off the bridge, and this trip, the total trip, is simply twice what happened in the last half. So that's a neat little shortcut sometimes you can use as far as if you need to find information like the maximum y value and such. Here is a motion map of an object that is launched up and out, and actually this object falls lower than what it started at. And so in the motion map, here again, remember you're seeing initial with the 0. That's just, again, standard format. So this particular object right here has been given both an initial up and an initial out velocity. And then every second, if it's traveling at constant, so this will be constant velocity here, that if it's traveling at constant velocity in the horizontal direction, notice that the horizontal arrows, the Vx arrows, all of them are all exactly the same. And if we look at it, the spacing of these motion dots, the position dots, should also be the same as well. What will not be the same is the acceleration component, which is the vertical component, where in the first half, the motion dots for the object are getting much closer together in a vertical fashion, and then after that, they are actually then going to be spaced farther out. So this one has a spacing of that, but these two have a spacing of this. Well, that's acceleration right there, and of course, it's acceleration due to gravity. And this object, at this moment right here, this is exactly the same height that it launched at. Because of that, whatever the initial conditions were, it has in the final conditions over here. At that moment, they're exactly the same, except of course down velocity instead of up velocity. And that's pretty cool. That's nice to know. But this object actually then falls further, and so we could then use simply the difference of the remaining 2 seconds to calculate what happened further, because we have, say, 2 more seconds of gravitational acceleration. So we could take a look at that as well. This is simply a different slide talking a little bit more about projectile motion, showing you some key points. If an object is launched at an initial angle of theta, then again 0 theta initial, with horizontal, the angle measured with respect to the horizontal. The analysis is similar, except the initial velocity has a vertical component, and that's all this slide actually shows. It is simply showing down here, and I probably ought to change the color to something a little bit more standout. It is showing that now we have an initial velocity right here at this angle. And that initial velocity, treating it like a resultant, has a vertical and a horizontal component that we can do trig on and figure that out. Then it just shows you at various stages. Because this object seemingly is landing at the same height that it started at, whatever the initial conditions were, the final conditions are exactly the same before impact, if you will, unless it's allowed to fall further down. Okay, so what are the equations that can help us with horizontal and vertical motion? Well, these are a combination of Unit 2 and Unit 3 equations with the trig brought back in, because now we have things happening at angles with each other. So that's all this is. This is just a variation of on this slide, this is Unit 2. On the next slide, it is Unit 3. Remember that Unit 2 is constant velocity. Unit 3 were acceleration models, to include free fall, of course. So what does this one say? Well, for objects that are launched at an angle, meaning they travel up and out, the initial velocity in the x direction, I think my pen is still activated, yeah. The initial velocity in the x direction is simply a factor, it's a component of the initial velocity. So if you let me see, I think I can draw it here. So if you imagine, you've got your parabola starting out, right? So if I have an initial velocity, so I'll just draw an initial velocity vector. So the object has this initial velocity, so VI. Well, the out component of velocity, Vx, and I get Vxi or Vx because it's constant, there is no initial or final states to it. That is a component from this angle, right? And so this is an adjacent side, and we can then use the cosine function as this is kind of arranged or oriented. And so that's why you see over here that it's a cosine function. So if I want to know Vx right there, I then just simply want to take the cosine of this initial velocity, and then I know the x component of that velocity. And that dictates the range. That and the time will tell you exactly how far away that object will land, all things being equal. And then rearranging down below, if you want to solve for x instead, what is the range? Well, simply just take the equation, and let me write it here. I think I can. Remember that velocity equals x divided by t, and we actually had delta x divided by delta t. Well, it's just then Vx equals delta x over delta t, no problem there. And also I do know that Vx is equal to the initial velocity. If we don't know Vx automatically, I know the initial velocity, and then I can run it through the cosine of the angle, and then I am right back to using those equations there. Down here, all this is just simply taking those equations, typing them, and rearranging them to solve for the displacement or the range, if you will. Okay, here's that soccer ball again, and all I've done on this slide is just I've grabbed the horizontal equations we just talked about a moment ago, and I put them on the left underneath the H for horizontal. And over on the right, I have a V for vertical equations. And what these equations are, my pen is still activated, so I can do this. These equations are Unit 3, and they are essentially free fall equations, but now there is an initial velocity in the y direction. So free fall with initial velocity, as opposed to, I think in Unit 3 we only did free fall without any up velocity at all. It was always just dropping something. Okay, so there you go. There's just a list of them. We will actually use some of these equations in a moment. Okay, these are just a kind of consolidation of those vertical equations without the soccer ball unit or the soccer ball picture. So it's the same thing. There's no real change here. But let's take a look at this for a moment. Pen is activated. So this is simply describing vertical velocity in the y direction initially. So what does it start with? That's what that describes, that VI sine of the angle. So anywhere in Unit 3, we see VIY or VYI, then this is the substitution for that, because that's what solves for the initial y velocity. Down here, this is on the second equation, so here we go. On the second equation, what is this? Well, this is simply a modification of VF equals VI plus AT. That's all that is. And it's just adjusted for free fall with initial velocity. And substituting acceleration in for A, we've just put G's down instead. Here, equation number 3, what is this? This is simply a variation of VF squared equals VI squared plus 2A, and because it's vertical motion, delta y instead of delta x, which is on probably your formula card, is the delta x. Here again, modifying for the initial velocity in the y direction, because now we're talking VYI, we have to make our substitution using the sine function. This last equation, in no particular order, but this last equation is a modification of delta y equals VIT plus 1/2 AT squared. I think it was a delta t squared. Acceleration due to gravity, so we substituted the g in, and remember now that we have initial velocity in the up direction, that's where that substitution using the sine function comes in. So that's all this is. That's all those equations are, and I would have a formula card, and I would update them and maybe notate them and talk about what they are. You never know if this formula card may come in handy maybe with the first test or so, if you ever take a physics class, it'll remind you of things maybe. Okay, moving on. So what I did was I grabbed out of your book a screenshot from, I don't know what the page is, but it's in chapter 3, and it's problem set E as an echo. And here are the 4 questions. There was a sample question completely worked out. It's in your book. You can look at that one. But what I would like to do is I would like to take these 4 and I would like to work them a little bit Khan Academy style, like I've done on the previous presentation, where I've got the interactive pen and we can talk through it together, or I can talk through it with you and hopefully make it make a little more sense than just something that is static and typed and already presented. Okay, well, here are the questions, and you'll see these questions again, so I will not read them at this point, but you can pause and take a look at them if you wish. But what I'll do is I'll work them with you, show you the substitutions, and talk you through it and get you a final answer. I will not bother to show very much plug and chug. If I can get you a final arrangement of an equation or a model, I trust that you can grab the numbers and substitute in and actually do that and cancel your units out. I'll give you the final answer, but that's what we're looking for. Okay, let's start with number 1. We have a stuntman, a stunt person in the movie. Okay, so example 1, movie stunt. What do we have? Well, over here on the left, I've actually already went ahead and listed my known variables. If I were doing graphs, this would be the given and then my requested. So I've got that right there. I've done a little diagram down here just to give myself a sense of what's going on. And I didn't bother to write in gravity, and I could. So 9.81 meters per second squared. That's a negative value. I'll change the color here back to yellow. I think I like yellow. So I read it again, I make my list of variables, and then I start to work through this. Well, what do I know? Well, I know, for instance, I have a lot of information in the x value, or in the horizontal, in the x, right? So I know that delta x is equal to the initial velocity multiplied by the cosine of the angle. I have the angle, and I have delta x. And this would be multiplied by delta t, because this is a variation of the equation of v equals x over t, and this is in the x direction. Okay, so I can rearrange this to solve for time, because I don't have time mentioned in any of my knowns, and that would be good to know as far as the time of flight. So time equals displacement divided by the initial velocity multiplied by the cosine of the angle. We have all of these values, so we can plug and we can chug, and if you do that, I hope that you run your own calculator and find, that's sloppy. I can fix that. There we go. equals 0.83 seconds. So that's the time of flight for this particular stunt person jumping from one building to another. And this is very interesting, and it's actually very practical if you're going to do a movie stunt. You're going to actually jump between buildings, like Tom Cruise does a lot of his own stunts. Back, especially before wire assist, before they had wires to help you out, so you actually could not fall to the ground, providing that the wires worked, that if you jump from a higher building to a lower building, you are able to make a bigger jump, if you will, because you can land lower and gravity is not working so hard against you, if you will, in order to try and land, say, at a building that's completely level with the one you just jumped at. So it really is an assist there. And this building happens to be 2.5 meters lower. So that's about the height of our classroom, by the way, if you're wondering what 2.5 meters, it's about the height of our classroom ceiling. And they're 4 meters apart, which is almost the width of our classroom, not quite. Our classroom is 5 meters wide, and this is only 4 meters. So just to give you a visual. Okay, so what are we trying to find, though? We're trying to find if he actually, like, how far below the roof level did he fall. So if I come down here to my diagram, if he starts here, even though he's doing a parabola, okay, so how far below this line did he fall? And actually, was he able to clear the 4 meters and land on the roof? Or is he actually going to be down in here somewhere where he smacks on the roof and doesn't make the stunt? Well, how we find that is simply by finding, how far he fell. So delta y. Well, delta y is equal to the initial velocity times the sine of the angle multiplied by the time. And this is a version. I'll tell you the version in a minute. Let me give you the equation. Plus 1/2 g delta t squared. Remember, this is a variation simply on delta y equals VIT plus 1/2 GT squared, allowing for initial velocity in the y direction. So that's all that is. That's a substitution. We now have all these values, and we couldn't use this until we solved for the time. But now that we know the time, we can plug and we can chug, and we can find that the answer is negative 2.3 meters. He had 2.5 to fall, and he only changed his height by 2.3 meters. So he was actually pretty much where I drew the diagram. He was right here, 2.3 meters, before after the 4 meter jump. He was at 2.3 meters, so he very easily landed on this roof and had no problem at all with the stunt. Fictional or not, and I've seen movies, from back in the 60s and 70s and earlier. Yeah, these stunts were actually done practically. Okay, moving on. I believe we've solved all that. Excuse me. Okay, here we go. This one is a golf shot. So we have a golfer going to hit a golf ball. 25-degree angle with respect to the ground, and if the golf ball covers a range of, or a horizontal distance of, 301.5 meters, which is a fairly good shot. That's actually a pretty good shot. What is the ball's maximum height? So, how high did this ball actually go? Now, there's an interesting hint here, and it's good to remember this, in that when some object is at the apex, at the very top, at the maximum height of its trip, that you can make some assumptions. And one major assumption is that the final y velocity, the final vertical velocity at that moment is 0. There is no up and down vertical motion or vertical velocity. So it's only horizontal velocity. So VYF equals 0 at that moment. Now that's not the whole trip, but if you consider that the whole trip, or at least half the trip, you can make that assumption. And at that moment, it's the maximum height. And so we also know that as well. Also, that typically happens halfway through the trip. And there are special cases where it doesn't happen halfway through the trip. But if it happens halfway through the trip, then you can do some math and actually double things and make that all that work. Okay, I'm going to pause for just a moment, take a drink of water, and then we'll get right into this question. You won't note any difference. Okay, I believe I am back. So with this one, I already have my givens all listed down. and I have my y max with a question mark. I forgot to put gravity down, so I just wrote g with a check mark because I know gravity. And where do we want to start? Well, let's let's take the hint and just remind ourselves of what the hint is saying. So at y max, we know that the y final velocity at y max, not as it hits the ground, but it is going to be 0, and this is at the apex or at the peak of the motion. So right down here at this point there. Okay, so what can we then say about that? We can say that the final y velocity is equal to the initial velocity times the sine of the angle plus gravity multiplied by the change in time, and all of this is equal to 0. So actually, you know what I could do? It actually looks better if I do it this way. So don't let me tuck the 0 there. Let me do it over here. So I can do final velocity in the y direction equals 0, which equals all of this. And this simply comes from, and I'll just tuck it over here quick, is VF equals VI plus AT, or VI AT plus VI. Either way it was written down on your formula cards. That's all that is. That's just a modification of that formula. Okay, so what we want to do, and this T is at the peak, so, or at the apex. So apex, let's just write that down. So let's solve for the time, because we don't know the time, and knowing the time of flight to get to the apex, or from the apex to the end, would be very useful. So let's just rearrange and solve for time here. So time at the apex equals negative initial velocity multiplied by the sine of the angle. I'm just rearranging this up here to solve for initial time, divided by gravity. Now I don't have values to substitute in yet because I do not know initial velocity, and I do know the angle, so I have two unknowns in this question, but this is a good arrangement. So as soon as I get an initial velocity, I can solve for the time. Alright, so what else do I know? Well, I know that at delta x total, and then delta x total down here on my diagram, is the entire range, and that's of course my 301.5 meters. And what do I know with the entire total range? Well, I know that at that moment the total time for the entire trip equals 2 times the time to get to the apex, because the apex is half the trip. So this is, it's half the time here, half the time there. Put them together, it's the whole time, and the whole time gets you delta x all the way over. All right, well, what we can then do is we can substitute in for time. And so, hang on, let me see where I'm at here. Lost my pen, just a second. Okay, I've got my pen back. Sorry about that, I had to pause. Okay, so what I can actually do then is, because time apex is down here and I have an arrangement of it right here, I can make a substitution. So I'm going to take that, substitute it in for time, the apex time, and this is what I get. The total time is equal to twice the negative initial velocity times the sine of the angle divided by gravity. And you could actually redistribute the negative sign out in front of the 2, which is probably more appropriate. And all I've done is I've just simply substituted in for the apex time. So I'm just trying to get rid of that aspect of it and bring in the whole trip here. And that time covers the whole trip with this information. Now I still am not at the plug and chug phase. I'm just trying to figure out a various substitutions or a variety of substitutions to get me to variables that I do know that I can plug in and actually solve for an answer. Okay, with also delta x, what do I know about delta x? Well, I know that the total range is equal to the initial velocity multiplied by the cosine of the angle multiplied by the total time. So I know that. Well, I can actually now make a substitution because I have a total time substitution. So I'm going to basically just bring this and this down and make a substitution. So if I do that, I'm going to kind of squeegee it over here. So I'm going to, combine these two, and let's write it over here. Okay, so I end up with delta x t equals vi cosine of the, this is horrible, hang on. Need a little bit more room there, so my apologies. And thank you for being patient and sticking with me. Or maybe you muted me and you can't hear me talking. Either way. Okay, so delta x t, so the total range is going to be equal to the initial velocity multiplied by the cosine of the angle multiplied by, see the time here, and I'm just going to substitute all this in. So let's just redistribute that -2 vi sine of the angle, all of that divided by gravity. So that's just a substitution is all that is. That's all that did. Okay, now I have this whole thing here, and it looks like there can be some simplification. So I'm just going to simplify down here. And by simplifying, it would look like this. So maximum range, the total range, is going to equal -2 times the initial velocity squared now, because I have initial velocity and initial velocity up here, so I just squared them to bring them together so they're in one spot, multiplied by the sine of the angle, multiplied by the cosine of the angle, so they just came together there, and all of this is divided by g, and this certainly looks better than the previous kind of spread out equation. If I want to solve for initial velocity, then I can simply take this and rearrange, and if I rearrange it, it would look like this. Initial velocity equals square root, because this is velocity squared, so square root of -g delta x divided by 2 times the cosine of the angle times the sine of the angle, or vice versa. Either way, it's the same thing. But you square root the entire quotient of all of this, and that is the initial velocity. That's pretty cool, actually. And I will say, this is a nice equation to have on a formula card because it solves for initial velocity, and that's that initial velocity here on whatever angle. And what do you need to know? You need to know gravity, which is a known. You need to know displacement, so you need to know the total displacement, and an angle. And so if you have these two values, you're gold. You've got enough variables to solve this, and now you know initial velocity, and that's even better because that leads to all kinds of other things that you can solve for. So this is a really nice arrangement, and this is why I took the time to go through all of these substitutions up here in order to show you this arrangement, because it is a very valuable model, even though it's not very intuitive on how you would get it. Where are you going to come up with this from a graph, right? Okay, well, we are really trying to solve for y max. We need to go a little bit farther here. So let's go a little bit farther. So what do we need? Well, we already had a y max up there, so let's bring that back down. So solve for, what do we have? So we have, let me change colors so it looks a little bit different. So let's do blue. Okay, so VF y squared equals vi squared sine of the angle squared. So that's just vf squared equals vi squared plus, 2ay or 2gy or something like that, plus 2 times gravity times the max y, so that's what we need, max y, and that's just a variation of, I'll sneak over here because I have a little bit of room. This is only a variation of vf squared equals vi squared plus 2a delta y, I guess, because it's vertical. That's all that is. And because final velocity at max, we talked about that, the very first thing, we know that equals 0. So because it equals 0, let me do this. I like to see that 0 actually out in front. So I like that, and that equals VF in the y direction squared. Okay, let's solve for y max. So we're just going to solve for y max. Y max equals negative vi squared times the sine of the angle squared divided by 2 times gravity. Okay, now I am running out of room quick, but I do have one final substitution, and this is substitute in vi squared into this equation. Where did vi squared come from? Right here. This was solving for vi, but if you square it, then just get rid of the square root, and then we have a substitution. So let's pull all this together, and that's that last substitution. So y max equals, and then substituting in, we are going to get negative g delta x over 2 times the cosine of the angle times the sine of the angle. I'll just dump that in parentheses because that's vi squared, multiplied by the rest of it. Well, the rest of it is just the sine of the angle squared over 2g, so sine of the angle squared over twice gravity equals, what do we have? We know gravity, we know the angle, we know gravity, and we know x. We know everything in this equation to solve for the maximum height that this object will actually attain. You can further, there actually is a further simplification of this, and it really looks a lot better, but this is a plug and chug, so I have no problem actually using it in this form here. The very final substitution, let me switch to a different color. I'll just show you really quick. It would look like x multiplied by the sine of the angle over 4 times the cosine of the angle. In all cases, whether you just use the one before it or that final simplification, 35, finally after all this, right, 35.1 meters is the maximum height of that golf ball shot. So right here, that height, that's what we've got. Now that we know the maximum y, we could actually go back and solve for the initial velocity, and we could solve for any unknowns at this point if we really wanted to. Okay, so that one was quite involved, but it was quite involved because we had a very valuable starred relationship right here, that equation, normally in the square root form that you would use. In this case, we ended up having to go backwards with it. Okay, feel free to pause, walk away, get a slice of pizza, come back, right? Example 3, a baseball throw. So a baseball, you can read the question there. We have an angle of 25 degrees. We have an initial velocity now, finally, of 23 meters per second. The ball was caught 42 meters later, so we have the range. The question is, what's the time? How long is it in the air for? And how high did the ball go, actually? So the maximum height as well. If we were going to solve this question, I've already got my knowns written down, and I have my question mark, and I forgot a gravity again, so I put gravity down. Oh, what do we have? We are looking for the time, so time of travel, right? Time of travel, and we are looking for maximum height. We have this time, though. We have that initial velocity, and we have an angle, so this is cool. So where do we go from here? Well, what do we know? Normally we start with some x material, so what do I know in the x? I know that the initial velocity, or the constant velocity in the x direction, is equaling the initial velocity along the angle multiplied by the cosine of that angle multiplied, let's see, I'm sorry, which equals delta x over delta t. We don't have the time. We are looking for the time of flight. And so let's rearrange this to solve for time. And so delta t equals x over the velocity, which is vi cosine of the angle. Well, let me see. We have the range x. We have the initial velocity vi. We have the angle. And so we can actually solve this one. And when we do, we find that it is actually going to be in the air for 2 seconds. And if it's going to be in the air for 2 seconds, we can actually use that information downstream. All right, so at y max, what do we know? We know that the final velocity in the y direction is equaling 0. So Vfy squared equals 0 equals Vyi squared plus 2 times gravity times the maximum y value. This, of course, has to have a substitution, so it really should look like, I won't write this Vf squared again, but 0 equals Vi sine of the angle, and that's all squared, so I have to square this, square that one, and square that one, plus 2 times gravity times the maximum y height. And I think I can kind of rearrange this and solve for y max. Okay, so let's just get things across the equal sign and isolate y max. And I'll move over here a little bit just to give myself some space. Okay, so let's subtract negative vi squared sine of the angle squared minus vi squared sine of the angle squared. So we just subtract that off, and that will equal, let's divide both sides by twice gravity. And if we do that, we have now isolated y max. Well, do we have these values? We have v squared, we have the angle, and we have gravity. So we can actually solve all of this without a lot of muss or fuss. Turns out that this height will only be 4.8 meters. Higher than the room, higher than the ceiling in the classroom, but not very high at all. Okay, so there we have that. Nothing really more to show on the slide. Let's go on to the last example 4, and I'm going through all of this in elaborate steps, so you are prepared for the problem sets. Okay, number 4. Here we have a salmon, and it's going to jump a waterfall in order to make its way upstream so it can mate and then die. Oh, just, these uplifting stories, right? So one salmon is going to start 2 meters away from a waterfall, and that waterfall is a little over ½ a meter tall. It's going to jump at an angle of 32 degrees. How would you like to be the person measuring all of this? Out there in the field with a tape measure and a protractor measuring salmon jumping. Oh, the life. So the question here is, what is the salmon's minimum speed going to have to be in order to get up to that upper waterfall? I have a very rudimentary diagram in the lower left-hand corner, not really to scale, but it's not actually all that bad. So we have the fish, we have the waterfall, and I've listed my knowns and included gravity. I just put a check mark there, but negative 9.81. And my question is, what is the initial velocity? Okay, so what do I know? What do I need to know? Well, I need to know the time. Most all these questions, it's good if we can discover what the time of flight is. So let me erase that stray mark, and let's go with that. Well, we can cut to the chase a little bit with the x component of things, and so I can just go ahead and tell you what the time is, right? So the time is the change in displacement over the velocity in the x direction, which is vi cosine of the angle. So that's just something that we know. We do not have any material that we can put in here yet because we don't have an initial velocity. So we're not going to be able to solve this, but this is a good substitution for time. So good substitution for time. Okay, what else do we know? Well, we know that the change in y is equal to the initial velocity in the y direction multiplied by the time plus 1/2 gravity multiplied by the time squared. And of course we have to put in the cosine function because of the angle, so really it's delta y equals vi sine of the angle delta t plus 1/2 gravity times squared. So that's really the arrangement that we use. At this point, we can substitute in for time. And so we have it in two locations. We have it there and we have it there, and we can substitute that in both times. So what is that going to look like? So let's just rearrange this, or rewrite it rather, down below and to the left. So delta y equals vi sine of the angle, and now I have to do a substitution for t. And that'll be delta x over vi cosine of the angle. So that covers this part of the function. Plus 1/2 gravity, and now I got to do the other time. It's the same substitution, but it's all squared now. And so what do we have? We have delta x over vi cosine of the angle. In this case, it's all squared. Oh, probably a little bit of simplification and distribution can go on now. So let me just drop down below and I will do that. I will distribute and simplify. So delta y equals vi sine of the angle delta x divided by vi cosine of the angle plus gravity multiplied by delta x squared divided by, since this is 1/2, I'll just put the 2 in the denominator spot, vi squared times the cosine of the angle squared. Okay, so I've distributed, and if I want to simplify, I see that initial velocity can go away there. Let's rewrite that. If I just give you these equations in their final form and I don't show you how you get it, then it's more problematic. I know this is kind of a pain to go through, but all of a sudden it's like I'm hand waving and it's magic. All of a sudden, it comes up there. It's like, well, what happened to the time? I just, all of a sudden time's gone. Where did time go? And this way, at least you can see why time is not in an equation anywhere. Because of substitutions and such. So take it for what it's worth. You'll see a lot of this if you get to college physics. Oh, and this, there was really no simplification over here, so maybe I didn't have to do this so much. But so 2 vi squared cosine of the angle squared. So that was not really there. Okay, so I can do a little bit more substitution, or not substitution, but simplification. And oops, how about an eraser? So delta y equals, looking at this function, I have sine, this function here, I have sine of the angle, delta x over cosine of the angle. Sine over cosine is tangent. So that actually can be simplified to tangent of the angle delta x. So that's a little bit cleaner. And sometimes in math class they call it a little more elegant, is what they call that. The rest of it didn't change, so I'll just lovely rewrite this thing again. 2 vi squared cosine of the angle squared. Rearranging because now I'm trying to isolate initial velocity, which is the whole point of this particular adventure. So I can subtract this from both sides. So let me go ahead and do that. So delta y minus tangent of the angle delta x equals g over. So that's that. And then what I want to do is I want to bring the denominator over across the equality sign and exchange out, because I have to get velocity out of the denominator spot. So that's all I'm going to do. So I would be multiplying both sides by the denominator here. So denominator, and over here as well, and then getting rid of that. And so that rearrangement will look like this. So 2 initial velocity squared cosine squared equals gravity delta x squared divided by, here is my, what is it, tangent of the angle delta x minus delta y. If you rearrange it, you would add tangent delta x and subtract delta y to get these across the arrow. Let's see here. There we go. And isolate VI, so all I got to do is divide by 2, divide by cosine of the angle squared, and then square root the whole thing. So VI equals square root of g delta x squared, or just delta x, I guess, divided by 2 times the cosine of the angle squared times the tangent of the angle times delta x minus delta y. If you plug and you chug, you should get 6.2 meters. Excuse me, per second. It's an initial velocity. So VI equals 6.2 meters per second. That salmon hits that 6.2 meters per second, it's going to make the waterfall and it's on its way to mate and die. If it doesn't, it'll have to try again, and hopefully it doesn't get so tired. Okay, so there you have it. Those are all 4 examples. I know this ran super long. I'm assuming you watched it in chunks and parts. There's just a little bit more to go, but I can go through this really quickly now that we've really seen a lot of not really plug and chug, but equation modeling, I guess. Okay, there's one final one. This is kind of a classic physics question that seems to come up in quite a few high school textbooks and quite a few high school physics classes. Has to do with the escaped monkey. Substitute any animal you want in. But an escaped monkey is found from a zoo hanging from a light post 5 meters in the air. A zookeeper, seeing the monkey, kneels 10 meters from the base of the pole, so you can kind of see the triangle there, and aims her tranquilizer gun at the monkey, because we got to tranquilize the monkey to get it back. The gun barrel, because you're kneeling and aiming at a monkey, would be about 1 meter above the ground. The monkey tries to trick the zookeeper by dropping a banana while still hanging on the pole. At the moment the banana is released, the zookeeper shoots. If the tranquilizer dart travels at 50 meters per second, will the dart hit the monkey? Will the dart hit the banana? Or will the dart hit neither? So what do we know? Well, we know delta y. Delta y is 4 meters because the monkey's at 5 and the gun was at 1 above, so the difference being 4, so that's the height the dart is concerned with, if you will. The range is 10 meters. That's how far the dart has to travel horizontally in order to hit something. And we know the initial velocity is 50 meters per second. This is all typed, so I don't have to write anything. Here's just a quick visual, a little bit of what you can see. Obviously, I just grabbed a bunch of clip art from the internet just to show the concept or idea of what is going on. Okay, what do we have to know? Well, we need to know the angle of the shot because we don't know the angle of the shot. We should know the time of the shot. How long is this dart in the air for? Well, how can we solve for the angle of the shot? Because we know two sides of that triangle, we can use the tangent function. We can use inverse really and solve, and we find that in this case, the angle is a little under 22 degrees. 22 degrees. The time of the shot we can figure because we have the initial velocity, and we are able to then solve for time because we know the range. And so just substituting in down below at this bottom slide, you see that the dart is only in the air for a little over 2/10 of a second. So during this time, knowing that as the dart left the gun 2.15 seconds, how far can a banana fall? Because they were dropped at the same time of the shot. So how far can a banana fall? That's free fall. That's like Unit 3 stuff. So free fall is just y equaling -1/2 gt squared. And so you plug and chug. Actually, it's 1/2 -g. So either way, you get it. And so the banana can fall a maximum of just a little over I guess 20 centimeters below the monkey. Okay, so we know where the monkey is. He didn't move or she didn't move. They're at the top of the light post 5 meters. We know where the banana is. Where is the dart? Is it in the monkey, the banana, what? Okay, so where's the dart as it travels up and out at 50 meters per second for 0.215 seconds? Well, y equals the initial velocity, of course, through the sine function multiplied by the time, less 1/2 gravity time squared. Plug and chug because you have all of those values, and it turns out that the dart is 3.76 meters higher than the gun barrel. Well, you add that 1 meter back in, and we now know the exact position of the dart with respect to the ground and the lamp post, and that's 4.76 meters above the ground. The banana is 5 meters less the 0.227 that it fell, so it's at 4.77 meters above the ground. It looks like the banana took the tranquilizer dart and the monkey got away. So that's a very classic physics example using projectile motion and kind of a silly scenario. But there you have it. I think there is just one more slide left. And that's just a kind of a summation slide showing you the two motions that we talked about. Both are projectile motions. One just happens to be more of a true parabola, and the other is a partial parabola. And the partial parabola is really where you have free fall and horizontal velocity, whereas a projectile with parabolic motion has both horizontal and vertical motion at the beginning of its motion. And you see a variety of equations there using the other symbology we talked about. Okay, well, this is projectiles. The next and last part of the presentation, part 5 now, instead on the last part of the section. We'll go very, very quickly. I think it's like 6 or 7 slides, and there's not much to do. So just realize when you get to that, it's not a marathon like this one was. So thank you for sticking with me. I hope you understood it. Go back and watch some of those examples. Check out YouTube. Go to Khan Academy. Look up a few of these types of problems, and they have them work there as well. And maybe they will explain them infinitely better and shorter than it took me. Okay, well, thank you very much, and I will see you in the last part of this presentation, and then I will be deploying, of course, work to allow you to practice this, some graded, some not.